The age of the Earth is 4.54 plus or minus 0.05 billion years. This dating is based on evidence from radiometric age dating of meteorite material and is consistent with the radiometric ages of the oldest known terrestrial and lunar samples. Following the development of radiometric age dating in the early 20th century, measurements of lead and uranium-rich minerals showed that some were in excess of 1 billion years old. The oldest such minerals analyzed to date, small crystals of zircon from the Jack Hills of Western Australia, are at least 4.404 billion years old. Comparing the mass and luminosity of the Sun to those of other stars, it appears that the Solar System cannot be much older than those rocks. Calcium-aluminium-rich inclusions, the oldest known solid constituents within meteorites that are formed within the Solar System, are 4.567 billion years old, giving an age for the Solar System and an upper limit for the age of Earth. It is hypothesized that the accretion of Earth began soon after the formation of the calcium-aluminium-rich inclusions and the meteorites. Because the exact amount of time this accretion process took is not yet known, and the predictions from different accretion models range from a few millions up to about 100 million years. The exact age of Earth is difficult to determine. It is also difficult to determine the exact age of the oldest rocks on Earth, exposed at the surface, as they are aggregates of minerals of possibly different ages. Development of modern geologic concepts. Studies of strata, the layering of rocks in Earth, gave naturalists an appreciation that Earth may have been through many changes during its existence. These layers often contained fossilized remains of unknown creatures, leading some to interpret a progression of organisms from layer to layer. Nicholas Steno in the 17th century was one of the first naturalists to appreciate the connection between fossil remains and strata. His observations led him to formulate important stratigraphic concepts. In the 1790s, William Smith hypothesized that if two layers of rock at widely differing locations contained similar fossils, then it was very plausible that the layers were the same age. William Smith's nephew and student, John Phillips, later calculated by such means that Earth was about 96 million years old. The naturalist Mikhail Lomonosov suggested in the mid-18th century that Earth had been created separately from the rest of the universe, several 100,000 years before. Lomonosov's ideas were mostly speculative. In 1779, the Comte de Buffon tried to obtain a value for the age of Earth using an experiment. He created a small globe that resembled Earth in composition and then measured its rate of cooling. This led him to estimate that Earth was about 75,000 years old. Other naturalists used these hypotheses to construct a history of Earth, though their timelines were inexact as they did not know how long it took to lay down stratigraphic layers. In 1830, geologist Charles Lyell, developing ideas found in James Hutton's works, popularized the concept that the features of Earth were in perpetual change, eroding and reforming continuously, and the rate of this change was roughly constant. This was a challenge to the traditional view, which saw the history of Earth as static, with changes brought about by intermittent catastrophes. Many naturalists were influenced by Lyell to become uniformitarians, who believed that changes were constant and uniform. Early calculations. In 1862, the physicist Lord Kelvin published calculations that fixed the age of Earth at between 20 million and 400 million years. He assumed that Earth had formed as a completely molten object, and determined the amount of time it would take for the near surface to cool to its present temperature. His calculations did not account for heat produced via radioactive decay or, more significantly, convection inside the Earth, which allows more heat to escape from the interior to warm rocks near the surface. Geologists such as Charles Lyell had trouble accepting such a short age for Earth. For biologists, even 100 million years seemed much too short to be plausible. In Darwin's theory of evolution, the process of random heritable variation with cumulative selection requires great durations of time. In a lecture in 1869, Darwin's great advocate, Thomas H. Huxley, attacked Thomson's calculations, suggesting they appeared precise in themselves but were based on faulty assumptions. The physicist Hermann von Helmholtz and astronomer Simon Newcomb contributed their own calculations of 22 and 18 million years respectively to the debate. They independently calculated the amount of time it would take for the Sun to condense down to its current diameter and brightness from the nebula of gas and dust from which it was born. Their values were consistent with Thomson's calculations. However, they assumed that the Sun was only glowing from the heat of its gravitational contraction. The process of solar nuclear fusion was not yet known to science. In 1895, John Perry challenged Kelvin's figure on the basis of his assumptions on conductivity, and Oliver Heaviside entered the dialogue, considering it a vehicle to display the ability of his operator method to solve problems of astonishing complexity. Other scientists backed up Thomson's figures. Charles Darwin's son, the astronomer George H. Darwin, proposed that Earth and Moon had broken apart in their early days when they were both molten. He calculated the amount of time it would have taken for tidal friction to give Earth its current 24-hour day. His value of 56 million years added additional evidence that Thomson was on the right track. The last estimate Thomson gave, in 1897, was that it was more than 20 and less than 40 million year old, and probably much nearer 20 than 40. In 1899 and 1900, John Joly calculated the rate at which the oceans should have accumulated salt from erosion processes, and determined that the oceans were about 80 to 100 million years old.